Today, we're going to talk about the characteristics of acids and bases and how we determine what is an acid versus a base. Now, an acid is known to have a sour taste, though I wouldn't recommend you taste anything in the laboratory. They are also known to be able to dissolve metals, and perhaps the most distinguishing feature between acids and bases is the fact that they turn blue litmus paper. Now, some examples of acids are, for inorganic acids, we have hydrochloric acid, which is hydrogen and chlorine together to form HCl. And this you've seen in Home Depot or any of your stores as muriatic acid. You use it to clean your pool or your patio decks and stuff like that. We also have sulfuric acid, which is what we call a diprotic acid because it has H2, so it gives off 2 protons. And nitric acid, which is one of the stronger acids that we use. Organic acids are found in like limes, lemons, citric acid, or perhaps malic acid, which you'll find in your fruits and such as apples and grapes. Now, these are some of the more common acids that you will run across in going about your day-to-day life. Now, bases are the other group that we are going to talk about. And bases, when you look at their characteristics, they have a bitter taste. Again, please do not taste them, but traditionally that used to be how it was determined. They also have a slippery, slopey feel, and if you ever feel a solution of sodium hydroxide, then you'll know that's what it feels like. And they change red litmus to blue. Note the slight difference between acids and bases. One changes blue litmus red, while bases change red litmus to blue. Now, in order to monitor the characteristics of acids and bases, we use indicators. And some of the indicators that we use are organic or from organic matter. Red cabbage is a very good natural indicator. And as you can see, you get a variety of color depending on the changes in pH. So if it's acidic, a solution from that red cabbage will have a totally different color in comparison to a solution that is basic. And here we show pretty much a wide gamut of what those colorations look like from a low pH to a high pH. And so you can use these vegetable dyes to determine whether the solution that you are working with is going to be acidic or whether they are going to be a basic solution. Now, litmus paper is an older form of water-soluble mixture of dyes that's added to paper, and you can use that to determine pHs as well, whether something is acid or basic. Now, phenolphthalein is another commonly used indicator, and we often use it during titrations, and it's one that you're going to see come across in most of your titration experiments. And in an acidic solution, phenolphthalein is colorless, whereas once more base is added, then it becomes a bright pink. And the shade of pink determines how basic the solution is. Now, acids and bases are based upon various theories, and we are going to spend some time to talk about each of these theories and describe the theories. The first of these is the Arrhenius definition of what an acid is, and this was introduced in 1887 by Svante Arrhenius, and he's a Swedish scientist that came up with this first theory. We'll talk a little bit about it later in the course. And then following the Arrhenius theory was the Bronsted-Lowry definition, which really was an addition to the Arrhenius theory, and it was given by Johannes Bronsted and Thomas Lowry. And the third and final definition is the Lewis definition, which was introduced by Gilbert Lewis in 1923. Now, let us take some time to talk briefly about each of these theories individually. Now, starting with the first theory, the Arrhenius theory of what acid is, or the Arrhenius definition of an acid. Arrhenius defined an acid as basically that they produce H plus ions when they are in aqueous solutions. This means consider an acid such as hydrochloric acid, which is HCl, and if you place that into solution, what you are going to have in that container is hydrogen ions, which is H plus, as well as the Cl minus ions. So as long as a solution produces H plus ions based on Arrhenius's theory, then that solution is an acid. And bear in mind, when H plus ions are in solution, they're extremely reactive. And so they tend to form hydronium ion, which is H3O plus, which is another way of writing H plus ion, as you will see later on. And this is called the hydronium ions. Now, Arrhenius defined a base as the opposite of the acid. It produces OH ions in aqueous solution. So a solution of, say, sodium hydroxide will always have Na plus and OH minus ions. So as long as OH minus ions are produced based on Arrhenius's definition, then that solution would be considered a base. And this was a very important early definition of an acid or a base, because in the early 1800s, basically it would just be a few acids or bases that would have been defined that early on. And so Arrhenius basically saw acids as just H plus ions and OH minus ions reacting. And later on, you will see how this definition has evolved. Now, when acids and bases react, they form a water molecule. Basically, H plus OH gives you H2O. And if you look at the typical acid-base reaction, the cation from the base is going to combine with the anion from the acid to make a salt. And that comes up with the term that we always hear, that acids plus bases is equal to salt and water. So if you look at a typical acid-base reaction based on Arrhenius's definition, then it's H plus OH is going to give you basically water, and then the anions and cations will combine to form salt. Example here is HCl with sodium hydroxide to form sodium chloride. Now, the Bronsted-Lowry theory did not take away from Arrhenius's definition of what an acid or a base is. It basically enhanced Arrhenius's definition. And his description of an acid, or their description of acid, is that an acid is a proton donor, whereas a base is a proton acceptor. Now, the base structure in a Bronsted-Lowry base must contain an unshared pair of electrons. And Basically, what this allows is that any reaction involving H plus that transfers from one molecule to another is basically an acid-base reaction, regardless of whether it occurs in an aqueous solution or if OH minus ions are present. And so any material could potentially be a Bronsted-Lowry acid. Now, the conjugate acid-base pair relationship is something that is very important. Basically, what it says is that in an acid-base reaction, the base, the starting base, will react to form the conjugate acid, and the starting acid will form the conjugate base. So we call each reactant and the product that it becomes a conjugate pair. In this example, ammonia is the base, and it gains H plus ions to form the ammonium ion NH4 plus, and that's its conjugate acid. Meanwhile, H2O is the starting acid, and it reacts to form the conjugate base, which is OH minus. Now, we call an acid a strong acid if, when it is placed in water, it completely dissociates to form its ions. So HCl completely dissociates to form H plus. So all the H plus concentration is equal to the concentration of that acidic solution. So therefore, if you had 1 molar of HCl, then you will have a concentration of 1 molar H plus ions. So hydrochloric acid, nitric acid, and sulfuric acid are examples of some strong acids. In a weak acid, you do not see complete dissociation, and so the H plus concentration is much, much less than the concentration of the starting acid. For example, acetic acid is an example of a weak acid. Also, you will have phosphoric acid, which is another weak acid, and carbonic acid. These are all weakly dissociated in solutions. The strength of an acid is measured by the acid ionization constant, or Ka, and Ka in a generic acid base reaction is defined by the concentration of the products over the concentration of the reactant. So for a generic acid HA, the Ka is equal to the concentration of the H3O plus ions multiplied by the concentration of the A minus ions, those are the dissociated ions, divided by the starting concentration of that acid. And this is another, it's the same way, HA dissociates to form H plus and A minus, and this is the generic equation for the Ka of an acid. Thank you for joining me as we talk about acids and bases, and good luck in this week.